Hi there. This is the first video of Chapter 8, Part 2. The notes are fairly straightforward, so we'll go through them fairly quickly. Some of the stuff we've already talked about in previous chapters, like this first bullet point. Chemical equation is always written using the form reactants on the left, products on the right, arrow in the middle. Arrow in the middle points from reactants to products. Chemical change, physical change, we talked about this last semester. And a chemical change is where we create a new substance. So if I burn a piece of paper, it is no longer paper afterwards, and it's created a new substance. In the case of burning paper, it creates ash. It's different from the original. Physical change is some sort of change where I don't change the substance. So if I melt gold, it's still gold. It didn't create a new substance. So that's physical change. Chemical equations. Let's say we have an equation like that. Basically, what the chemical equation is, it's kind of like a recipe for a reaction. And it tells us what's in the reaction, so which chemicals, in this case hydrogen and oxygen and water, and it tells us how much of those things we have. So it's basically a recipe. We will come back to that more so next chapter. The next thing in the notes here, state changes, or sorry, state symbols. And if I were to write H2 and put a little G behind it, what that means is hydrogen gas. If I wrote H2O and put a little liquid, well, L standing for liquid behind it, sometimes you'll see it as a cursive L. That means liquid water. If I put a little S behind something, it means solid. So here I have solid silver. And lastly, we can have something called an aqueous state. And that is basically we have something dissolved in water. So if I take the compound NaCl, table salt, just like the stuff you put on your popcorn, normally I would have an S behind that because salt is a solid. Now, if I take that salt and I put it in water, I would write that differently. I would write NaClAQ, and that AQ tells everybody that this stuff is dissolved in water. So NaCl with the AQ after it is a fancy way of writing salt water because that's what this is. It's salt dissolved in water. The next little bit of notes here are the diatomics, which you should have learned for the last test. If you didn't, you'll again want to learn them for this coming up test. Now the main part of the notes here, and the main one of the main parts of this unit, are these 5 reaction types. RxN is the abbreviation I'll use for reaction. Over the next couple chapters, you'll be writing the word reaction a lot and save you a little bit of time. Just use RxN. I'll know what you're talking about. Everybody in class will know what you're talking about. So there are 5 types of reactions that we're going to talk about in this unit. There are more, but these are the 5 we're going to focus on for this unit. First one is synthesis. Synthesis is a fancy word for taking simple things and combining them. So in this case, we are taking 2 elements and combining them to form a compound. The basic format is a simple thing, create a compound. And then I have an example here. Hydrogen plus chlorine makes, this is actually hydrochloric acid, which we'll talk about in a couple chapters. But hydrogen chloride is how you could name it if you wanted to. So that's synthesis. Decomposition is the opposite of synthesis. And you probably remember back from biology class, you talked about this word decompose, decomposers, decomposition. And in that context, if an animal or plant dies, they decompose, meaning that various organisms and critters eat this dead thing and break it down into simpler things. Eventually, that plant or animal becomes dirt. Very simple, basic things. So we have a compound and we break it up into the individual elements. And you can see that here. We have mercury and oxygen, and they break, and they're a compound there, mercury oxide, and they break up into mercury and oxygen separate things. So notice synthesis and decomposition are opposites, and I think that's even a book question answer right there for you. The next one, combustion. Combustion doesn't really follow a pattern like the other four do. Combustion is a very specific type of reaction. It must be a hydrocarbon, and a hydrocarbon is something made up of hydrogen and carbon. And we can say that here, C2H6, that's our hydrocarbon because it's made up of carbon and hydrogen. We react that with oxygen, and it's always oxygen, and we always form CO2, carbon dioxide, and H2O, water. So again, for these other four, you're looking more of a general pattern, but for combustion, you're looking for specific chemicals. A hydrocarbon and oxygen on one side, carbon dioxide and water on the other side. The next two, or the last two here, types of reactions are single replacement and double replacement. That's usually the term that I will use. I will tell you the book uses, instead of replacement, they use displacement. So for single replacement, they just call that displacement. For double replacement, they'd call that double displacement. Replacement, displacement, they mean the same thing. I think most books and most teachers in your future will probably use the term replacement, but just be aware. Basically, they mean the same thing. Now, it's kind of good that we have Jack of Hearts coming up, because some of the stuff we're going to talk about here kind of makes sense if you put it into kind of a dance scenario. And for single replacement, the way I remember this is we have a couple dancing. In this case, A and B are dancing, and we have somebody that's single. And what happens is the single person comes in and kicks out one of those two dancers, and now C is dancing with B and A is all alone. So again, you have a couple dancing and somebody alone, and the one that's alone comes in and buds in. And you can see that in the example. We have sodium and oxygen dancing. Here we have potassium. Potassium comes in, knocks sodium out. Now potassium and oxygen are dancing and sodium's all alone. This dance scenario kind of works for double replacement too. In this case, you have two couples dancing, and then they switch partners. So we can see that here in the example. We have sodium and phosphate. Phosphate is referring to polyatomic ion sheet. Those are dancing. Here we have lead and nitrate, and again, nitrate is also from your polyatomic ion sheet. So we had two couples dancing, and they switch partners. If you notice on the left, sodium is with phosphate. Over on the right, sodium is with nitrate. So those are the 5 reaction types that we're going to focus on for this unit. And now you get to try some on your own. So you don't have to copy these down or anything. I'll go through these kind of in chunks, however many I can fit on a page here. And actually, let's see here. I'm going to pause it 1 second and make this bigger. So what I'll do is, if you want to look at these, if you want to pause the video here, look at them, figure out which type of reaction is it. Which type of reaction it is. Well, is it synthesis? Is it decomposition? Is it single replacement, double replacement, or combustion? And again, you can look at those notes from before and try and figure out. You're looking for a pattern for most of these, with the exception of combustion, which you're looking for specific chemicals. Hydrocarbon, oxygen on one side, CO2, H2O on the other. So if you want to pause it now and then do these, and just number 1 through 12. So number 1 through 12 real quick, and then just go through and say number 1 is whatever you think it is. C for combustion or SR for single replacement. And then unpause it and I'll go through the answers. So pause it now, do 1 through 12, and then I'll go through the answers when you're ready and you unpause it. Okay, so hopefully you've gone through and done 1 through 12, and basically I'm just going to give you the answers here. Number 1, we have a compound and it's breaking up into simpler things, so that is decomposition. If you notice, number 2 is the exact opposite of number 1. And so what we do there is we are taking two simple things, in this case hydrogen and oxygen, and making water. So that is synthesis. So the first one, decomposition. Second one, synthesis. Third one, the most common wrong answer will be single replacement, because it kind of looks like a single replacement. It has a couple dancing, carbon and hydrogen, and then oxygen. But if you look on the other side, it's got two couples dancing, so that doesn't fit the pattern of single replacement. Once you notice that, oh, I got a hydrocarbon here, carbon and hydrogen, oxygen, and then on the other side of the arrow, CO2 and H2O, you realize that is combustion. So 3 should have been C for combustion. 4, we have two couples dancing, aluminum and sulfate, and calcium and hydroxide, and they switch partners. So number 4 is double replacement. Number 5, we have two simple things. Here we have phosphorus with nobody else, oxygen with nobody else, and they come together and they make a dancing couple. So that is synthesis. Number 6, here we have potassium and phosphate dancing together, and lithium's all alone. Lithium comes in, knocks it out, and so that is single replacement. We have a couple dancing and somebody that's single, so single replacement. Next one, hydrocarbon, oxygen, carbon dioxide, water, that's combustion, so 7 should have been C for combustion. 8 is decomposition. We have a compound splitting up into simple things, so 8 is D. Number 9 is another single replacement. Here we have Na alone, Mg and O are dancing, Na comes in and kicks Mg out. Number 10, a compound breaking up into simple things. That is decomposition. Number 11, we have hydrogen and phosphate dancing, magnesium and hydroxide dancing, two couples dancing, so that's double replacement. And lastly, H2 and Cl2, two simple things coming together to make a compound, so that is synthesis. So hopefully that went well, and at this point you can take the practice quiz on reaction types. If you have any questions, send me an email, stop in during first hour. Thanks.